Today, we talk about overcoming bottlenecks in aircraft development by testing on power level. Hello and welcome to another dSPACE Learning Bits. I'm your host, Mike Neumeier. Today, I'm speaking with Sören Reglitz, Product Manager for Aerospace and Defense at dSPACE, and Manuel Fischer, Business Development for Electromobility and Electric Drives at dSPACE. Hi, Sören. Hi, Manuel, and thanks for joining me today.
Hi, Mike. Thanks for having us.
Hi, Mike. Thanks for the invitation.
Absolutely. So first off, please explain what are the challenges when developing new aircraft today?
Well, Mike, traditionally, the aerospace industry is heavily regulated and strongly driven by standards. This applies to every step of the aircraft lifecycle, from development to manufacturing to maintenance and operation. In particular, the development process follows a very formal and requirements-based approach, covering both functional as well as safety-related aspects. When it comes to avionics, the challenge is to establish confidence that every item of software and electronic hardware on board the aircraft performs to its design requirements. As outlined in Aerospace Recommended Practice 4755A, this calls for a very thorough process for requirements allocation and validation, shown here on the left side, and subsequent integration and verification, which you can see on the right side. This process is also applied to new aircraft designs, of course, targeting all-electric or hybrid propulsion and more electric aircraft systems in general, which require all a growing amount of complex onboard software. On top of that, one major challenge in developing these future aircraft is managing the distributed organization of system development done by either multiple internal or external suppliers. Managing this supply chain while meeting required targets for time, cost, and quality is extremely challenging.
What are the bottlenecks when it comes to testing?
Well, as you can see, the implementation is followed by several integration steps, up to ironbirds and aircraft prototypes, which are managed by the aircraft manufacturer. Each of these steps includes a verification phase for thorough testing on item, system, or aircraft level. One major goal of testing, of course, is to find defects as early as possible in the development process. However, as I mentioned before, there are multiple stakeholders involved in this integration and test phase, often including suppliers from different organizations. This introduces additional risks in the test process and requires flexible test means that can actually cope with delays in the supply chain. One well-known solution to this problem is virtualization of missing system parts by simulation on signal level, which we all know under hardware-in-the-loop testing. But to take it one step further, you can also emulate those parts on power level. This greatly expands the range and depth of tests you can perform in early development phases, even if a lot of real parts from the supply chain are still missing. In addition to that, test means can be easily reconfigured and reused to emulate different variants of an electrical machine on power level.
Very interesting. Thank you, Sören. So, Manuel, how can dSPACE help avoid these bottlenecks in testing?
The dSPACE hardware-in-the-loop tools enable hardware testing in a very early stage of the development process, even if components like inverters, motors, or batteries are not available yet. These missing components will be replaced by a real-time system, which is designed to have the same electrical characteristics as the corresponding emulated part of the drivetrain. This emulation can be elaborated either on a signal level or on power level. I'll give you an example. In the first development stage, the current control system for a three-phase inverter is implemented. The inverter drives a three-phase machine. The control system calculates the output voltages of an inverter as actuating value and determines the firing signals for the inverter's semiconductor switches. A dSPACE signal hardware-in-the-loop system can be used to test the control system in this early development stage, even if the inverter is not available in hardware yet. The hardware-in-the-loop system reads the firing signals and calculates the inverter's behavior in combination with the load in real time. The resulting phase currents values are converted into the signal scheme of the current sensors and fed back to the control system. Going one step further. In the next development stage, the inverter is also available in hardware and has the purpose to drive an electric machine. If the real machine is not available at this point, a dSPACE power hardware in the loop system can emulate the machine's behavior on power level. By measuring the inverter's output voltages, a real-time model evaluates the machine's electrical and mechanical behavior, especially the time response of the phase currents. These values serve as reference currents for power electronics actuators that adjust the three phase currents in that way that the same phase currents occur as in the setup with the real machine. The inverter and its control algorithms can be tested at full power level.
Thanks, Manuel. Last question. Can you show us how a Power-Hil test system looks like and what solutions dSPACE offers?
Of course. The power hardware in the loop system consists of three major components: real-time models, a hardware in the loop system, and power hardware in the loop hardware. At first, real-time models calculate the behavior of the emulated parts. In the previous example, the measured output voltages of the inverter are analyzed by the model, which calculates the course of the three phase currents and mechanical values like torque or speed of the virtual machine. dSPACE offers different types of open real-time models, either processor-based or FPGA-based, if a very fast calculation is required. To run these models in real time, corresponding hardware is required. The modular approach of the Scalexio lab box is predesigned for this purpose. Cutting-edge real-time processors and FPGAs, as well as comprehensive I/O functionality, can be integrated into the lab box. Thus, with these two components, signal hardware in the loop testing is possible. The transition from signal level to power level is seamless by adding power electronics actuators, the so-called load modules. dSPACE offers two types of load modules for low voltage and high voltage application up to 1250 volts. Due to the fact that each module is independently current controlled, the modules have a behavior like a highly dynamic current source. Multiple modules can be connected in parallel, so the overall system power is scalable by choosing the desired number of modules. This box shows the setup of a 500 kVA system, which emulates a high voltage battery and a three-phase machine. In the right cabinet, the Scalexio real-time system and a high voltage supply is integrated. In the two cabinets in the middle, the load modules are housed. The inverter, as device under test, can be placed in the left cabinet. All in all, with this setup, we are able to emulate the battery and the machine on a power level so that the device under test is not able to distinguish if it's connected to the real components or the power hardware in the loop emulation.
Thank you again, Sören and Manuel, for speaking with me today and answering some important questions on this topic. For all of you watching, please feel free to visit our website at www.dspace.com and submit any questions or topics that interest you. Don't forget to hit that like and subscribe button below and follow us for more exciting content. Have a great day, everyone.
dSPACE, your partner in simulation and validation.